In the third part of the course, we're going to be dealing with equations, formulas, and ratio and proportion. So each of those topics we're going to spend a week on. So this week's lesson is based on Chapter 9, which is solving equations. I think that this topic, after writing a test, it's a nice topic to start with. It's a lighter topic. Nothing too dangerous here. There is some algebra here that might be a little bit more new for some people. Maybe they haven't done it in a while. But for the most part, I think that you'll find today's lesson fairly easy. We're going to cover sections 9.1 through 9.4. We'll take a break after section 9.2. And ultimately, the first three sections are just algebra with and without diagrams. Section 9.4 talks about looking at an equation and figuring out if it's possible to have solutions or not, or how many solutions there might be. And then you get into Friday's class, which will be on roots and powers and also equations involving measurement. So without delay, let us talk about section 9.1. In section 9.1, which is just as the basics of solving equations, what you're really looking for here is the golden rule of algebra. Anybody know in the chat here, what is the golden rule of algebra? What's the golden rule of algebra? Anybody heard of the golden rule? I mean, it's not like a formal rule, but basically it says whatever you do to one side of an equation, now let's say it better than that because that sounds very unprofessional. Whatever operation you perform on one side of an equation, you must perform the same on the other side. Yeah, I never heard of it as the golden rule until I started talking with some of the other math professors. And they're like, yeah, golden rule, golden rule. I'm like, golden rule? I'm thinking golden rule is like when you're, being nice to people and do unto others as they do unto you and all that stuff. But they were getting all like, philosophical on me there. But anyway, yeah, golden rule of algebra. So, yeah, anyway, we're going to call it the golden rule of algebra. It just sounds cool. We can make up our own rules as long as we get the right answer. Is that how it goes, I guess? Anyway, all jokes aside, let's do some questions here, but we're going to abide by this rule. So you can actually, I would recommend that you read through the first few pages of the book here. The author does an excellent job talking about the ideas and the logic of equations and what you're trying to preserve in terms of equality. There's several examples that they go through. And instead of me rehearsing the examples with you, I'm actually just going to go to some of the exercises. So these exercises can be found on page 7. And if I just go here to page 7, so here's page 7, there's 5 questions. And we're going to go through all 5 of those questions now. So these equations here, these all have one thing in common. I'm just going to make a note here. These are all linear equations. Okay, first I need to learn how to type, and then I'm going to talk about Matthew's comment. Matthew, you're way ahead of me, so I got to catch up to you there. But anyway, we're talking about linear equations. So linear equations are something that you need to be very comfortable with because they're very common in everyday life. Even if you're like, oh, I don't solve equations in everyday life, you do. You just don't really phrase them as equations, but you do solve equations. You're always solving equations. When you're calculating anything involving, whether it's a tax or, you know, rate of pay or speed or getting somewhere on time, these are all equations that you're solving. You just haven't phrased them as equations. But anyway, I'm going to go through these questions really, really slow. So if anybody here gets bored, I apologize, but I don't want to lose anybody in this conversation. And like I said, we're going to start off nice and easy because look, you just wrote a test last week, and we can just take it easy today and not really just destroy anybody. I'll write down the steps on each line so that everybody is clear about what's happening here. So in the first step here, we're gonna look at this equation and say, well, we want to isolate x, but the thing that's in the way is the 12 and the 3. So what should we deal with first? I know these are really easy questions, but we're gonna go slow. What should we get rid of first, the 3 or the 12? What should we deal with first? So actually the answer is you can deal with either, but yeah, Matthew's opinion is actually the most common opinion, which is to get rid of the 12. You might say, could I have gotten rid of the 3 first? Yeah, you could have. I'll show you how. But first, let's just get rid of the 12 because this is the way that you should do it because it's faster and it doesn't involve fractions. 45 minus 12 is 33. And then how do you get rid of the 3? Well, 3 is multiplying the x, so the opposite of multiplying is dividing. And that's how you get the answer, which is exactly what Matthew wrote down. So thank you for that, Matthew. But I just mentioned to you that you could have solved this the other way, which is to divide by 3 first. I don't recommend dividing by 3, but I'll just do it here just for like enrichment. So the idea here is that if I want to get rid of the 3 first, 3 is multiplying the x. So what I could do is divide everybody by 3. So I wouldn't recommend doing it this way. I'm just showing you that it is possible. So what I'm doing is dividing both sides by 3. Equivalently, I'm dividing all terms by 3. You know, it's weird, but sometimes it's better to deal with the multiplication or division first. And I know that's not natural for most people to do, but it is actually a feasible way of solving this question. I do believe they do, Sheldon. It's just that the thing is, in real life, the numbers aren't pretty. So these types of equations, really, the numbers you're not getting here are realistic, but we're just focusing at the moment on the foundations of the algebra and really just getting a handle on all the building blocks that you need. What happens is, no, it's good. It's a good point. It's a good point, Sheldon. You see, the thing is that the design of this course and the design of the course in the next semester, Math 1146, its objective is for you to see all the math that you should know how to use in your program. Granted, the Math 1146 stuff is a lot more practical. The stuff that you're seeing here, because we're just making sure the foundations are all there. Yeah, it's really hard for me to tell you about a real life question that looks like this, but I can give you a question like that. Makes sense. These type of equations, I'm going to talk about James' comment there in a second. These types of equations in real life, where would you see them? Anytime that you have, for example, a fixed and a variable cost. That's a very common situation. Can you think of anywhere in real life where you have a fixed and a variable cost? Let's talk about renting equipment. When you rent equipment, there's two aspects to it. Whether you're renting a vehicle, for a project or some type of an apparatus, or maybe it's an instrument that's measuring something. These things have a fixed and a variable cost associated. For example, if you rent, let's see here, I don't know. I'm trying to think of an equipment piece that I've used in my life. I mean, not serious construction stuff here, but like a cement mixer, right? You might have a fixed cost for the actual rental when you take it out, and then a daily rate of holding it. So maybe you pay $100 up front, and then you pay $70 a day. Let's say you're doing a small project at home or something. So you see that fixed and variable cost fits in right here. The 3 would be the variable cost, and 12 would be the fixed cost. You know, I'll put a question. I'll try to make the question on your assignment to be more like everyday life kind of questions. So they're not just going to be plain numbers. I'll give you a question that you can set up with algebra, but it has a connection to everyday life. Now, James's comment is very nice actually. So James, when I have a question, I mean these questions, relatively speaking, would be fairly easy for me, obviously, like because I'm teaching you this stuff. But when I find questions that are really hard that I'm not sure how to solve, what I usually do is make a guess, just like you, and then I see if my guess is pretty good, and then I adjust. And that at least, not necessarily trying to guess the answer, but at least providing an estimate. Okay, we're gonna keep on going now and just talk about the next examples. So in this example here, one option would be to move the 3 over, or the other option would be to multiply everybody by 2. Both options are really nice, but I'll go with the former, which is just to move the 3 over, because that typically is what most people would do anyway. So let's do that here. So we would move the 3 over. When I say move the 3 over, what I'm saying is the opposite of subtracting 3 is to add 3. This gives the illusion that these guys here go away and that the 3 has quote unquote moved to the other side. So in future steps, what I might do is see the stuff in red. I won't write the stuff in red in future steps because you're literally just moving it over as a pattern. When someone says you're moving it over, it's not really moving it over. It's actually just it's an observed pattern. What do we do on the next step? How do we get rid of the half? What would be the operation that would neutralize the 1/2? What operation would neutralize the 1/2? Yep, double by 2. Thank you. I'll use a dot here. Yeah, because that's dividing by 2, so we want to multiply by 2. So I'm going to use the dot operator. This just means multiply. You can appreciate why I don't want to use this symbol here because it looks like an X. So I use a dot. You can use brackets. You get 38. You might be like, what if I want to get rid of the fraction first? Could I get rid of the fraction first? So I'll make a note here and say that in this situation, what we did was we dealt with the subtraction first. As an option. Make it present tense. In this case here, I'll deal with the division first. And you can, and I'll kind of quiz you after. I'll ask you, what do you feel? In this case here, okay, it's not really a fair comparison because the numbers are larger here. But one thing you could do here is multiply everybody by 8. And that's an alternative that some people prefer. People, like for example, I like to get rid of the fraction. Because for me, the thing that I know that if I'm going to make a mistake somewhere, it's going to be with fractions. Usually with equations, it's the fractions that get me. Because nobody's perfect. So anyway, I multiply everybody by 8 because the rule is that whatever you do to one side, multiplying by 8, you should do to the other side. So in this case, you would get here x minus 8 times 15 is 120, because it's 80 plus 40. And then you have 80. Then that equals, understand that the numbers are larger, and you might say, oh, this method is not as good because the numbers are bad. This is a consequence of the numbers being very large. But anyway, don't judge the method based on the numbers being larger, but just give me your opinion if you don't mind. Which way did you like better? Did you like the first way here or the second way? I want to get a feel for how you like to do math. So what do you like, the left one or the right one? So you see that we have people saying mostly the left. There's a few people that say the right, or one person said the right, including me and Cosmo, I guess. Norris is on the fence. It really depends. It depends on what you like, okay? How come you divide on B? Where did I divide? Are you talking about this, Cosmo? Oh, you're multiplying by 2 because see this x half x or whatever, it's really x divided by 2. You can think of it as x divided by 2. So when you have x divided by 2, that you see how it's a division now, and then the opposite of division is multiplication. So you're applying multiplication to neutralize it. All right. Now this question here, this is a situation where the left versus right comparison. This is a situation where I would actually multiply first. So how I did the question on the right. So in all honesty, which way is better? They're both good, but sometimes it's better to multiply first. It just sometimes, rare occasions. Like over here, for example, you see all of these guys here, they're all decimals, and I don't know about you, but maybe you're not a fan of decimals. We could multiply everybody here by 100. Now, I'm really trying to emphasize here that I'm trying to do the questions without a calculator. So if you're using a calculator, that's fine. But a lot of the arguments that I make are under the pretense that you are not using a calculator. Anyway, 100 is a good number because it'll clear out the decimals. But if you do a number that you could use instead, though, that would be better, is 20 if you have a calculator, because 20 would turn these all into whole numbers. But I'll just multiply by 100 just because I think it's just quicker. So by hand, I mean. So 5x minus 185 is 75. And then we can move the 185 over. So you can see here I'm writing a little bit less now, getting more into a groove with it. So what is that, 260? And then you can divide by 5, and that's 52. The whole objective was here is that when I'm teaching you, or just not even teaching you so much, reviewing it with you, most of you can solve these anyway. I'm reviewing it with you the way that I would do it without a calculator. Anybody want to confirm this answer? This is not a dictatorship. Anybody have the same answer? Thank you. Thank you, Nicolos. In question E, again, we could move the 40 over and then divide by 4, or we could divide everybody by 4. I'm going to just move the 40 over because that was the consensus with most people when I polled you earlier. So how about this? Yeah, you would have the same answer, but you would have nicer numbers. That's the only thing. Like you would, these numbers, see these numbers here, they wouldn't be as large. That's all. But I think 100 is just a safer bet, so that's why I'm not going to experiment. I don't want to experiment with something, especially if I'm doing mental math. I don't like to experiment with mental math. I just want to play it safe usually. So in this case, you have a negative answer, which is fine. I'll write down the step. and eventually you should get that. Anyway, there's some questions to start with. Hopefully you see something in there that, yeah, absolutely, Matthew. And Matthew, in all honesty, we're doing the same thing. And for people here that have dealt with like a lot of accounting or exercises or bookkeeping or anything like that, this is money basically, okay? This is 75 cents plus $1.85. If you're used to dealing with numbers like how you deal with money, then this stuff is light work. But but then again, if you're someone here that is not really like as quick with decimals, which is fairly normal, then you want to do whatever you want to write the equation in a way that is easiest for you to play with. So what I'm really ultimately saying is I've shown you things here and there through the 5 examples here, and they weren't all solved the same way. I tried to experiment a little with you so that I could get a feel from you how you like to do things. So as we approach questions later on in this booklet, I'm gonna just try to do the most common way to do things. But if there's an opportunity where I can show you something interesting, I might repeat the same question twice and show you an alternative for how to deal with it. So that's section 9.1. Really, as far as you're concerned, it's just talking about what is the fundamental type of rule in dealing with algebra, with equations. Whatever you do to one side, you do to the other, with the ultimate objective of isolating the x, or the variable. And pretty much for the rest of today, I think the variable is always x, at least for the first hour. But definitely next week, we're going to have a lot more fun. So, sorry, yeah, with all the formulas that we're going to be doing. So anyway, we're going to move on to section 9.2. And as you might imagine, if 9.1 was very simple equations, then 9.2 is more complex equations. So these are equations that have more terms, or perhaps there's extra coefficients, just things that make a little bit like annoying. So let's see some examples here. So as you can see on the following pages, there are several examples that the author goes through. They do an excellent job, and I'm going to do similar examples just to the exercises, so that way I'm not repeating what the author is already explaining to you in the book. So anyway, I've chosen from page 11, there's 5 questions. We're going to go through all 5 questions. If there's time remaining before the break, we can try some more, and we just keep on going. So let's go to, this is page 11. So I'll just make a note here, page 11. So here's your first example. We have 6x minus 21 is 2x plus 31. What's the first thing that we could do in this question? Yeah, you can move the 2x over. And what about the 21? Yeah, bring that over as well. So let's do that together here. So we're going to take this guy here and move it over. So don't mind me, I want to just highlight the things, the terms as we move them around. So we would have here 6x. As the 2x moves over, it becomes negative 2x. And as we move the negative 21 over, it becomes positive 21. This gives us 4x is 52. To get rid of the 4, we divide by 4. If you've played cards ever in your life, you should know 52 divided by 4. I had a conversation I was at my friend's place the other day, and their kid was there, and they were doing a math question. There's 52 divided by 4. I go, do you play cards? I asked the kid, what's 52 divided by 4? They're like, I don't know. And then I say, do you play cards? And then the kid's like, no. I go, there you go. So if you play cards, you should know 52 divided by 4. I'm not encouraging playing cards, but like, not that there's anything wrong with that. There's lots of good um, games with logic and strategy. Anyway, the next question, I suppose that at this point the numbers are starting to get a little bit out of hand. So maybe this is a point where I might resort to a calculator, but I would do it with when all my effort is basically to a point where I'm like, okay, I don't feel like doing this by hand anymore. Because I sure as heck don't want to do long division. So anyway, in this question here, we could multiply everybody by 100, or we could just leave it as decimals, as Matthew mentioned. And both ways are fine. So what I'll do is I'll just leave it all as decimals because that shouldn't be too dangerous. And in all honesty, if I was a student doing this, I would use a calculator anyway. 1.74x. We'll move over to the 0.57. And then you'd have 0.98 plus 4.23. Now, I write the 0 on the decimal. I understand that a lot of times in construction and in related disciplines, people just write 0.98 or point whatever. I need to write it like that so that I do a thorough explanation. Is that the final answer, Matthew? I haven't gone that far yet, sorry. Okay. All right, I'm gonna catch up to Matthew, but you guys help me out here because I'm not using I don't have a calculator. Minus 0.57. So what is that? Is that 1.7? Sorry, Norris? I thought Norris said something. Sorry. There was a little bit of feedback on my mic, and what happens is the last person that touched the mic or whatever, their name shows up on my screen at the bottom. So maybe that was a little glitch anyway. Sorry about that. Can anybody agree with these numbers? Thank you, Matthew. So you're saying 5.21 divided by 1.17? Yeah, it's going to be something a decimal. Okay, I got you. I'm going to go grab my calculator. Just give me a second. Okay, all right. So it wasn't too far away from me. Anyway, in this case, unfortunately, we're going to have to do some calculations of decimals. So yeah, unfortunately, it's not mental math. It could be mental math. You might be like, well, how would you do mental math with this? I'll show you. The nice thing about these questions is that I don't rehearse them before the lesson. I don't like to know the answer before starting with you. But if you're like, how would I do this by hand? It'd be long division, unfortunately. But how could you do a quick estimate of this? If you're wondering how would I do this in my head, or at least most of the question in my head, the first thing I want to do is I can't talk and type, so you're gonna laugh at me right now. Yeah, you could do a 2-digit approximation. So the first thing that I do is kind of just list multiples of 117 in my head. And essentially what I'm doing is long division in my head. I'm pretty much just doing long division in my head. So what I'll do is I'll do 521 and I'll count this way. I'm just counting with 117s, and that's 4 of them. And then from 468 to 521, that's 53. So then 53 means that I'll have 530. So then 4 of those go into 530. And then 530 to 68, 468 is 62, which means I can have a five of them in the next iteration. Literally, that's what I'm doing. I'm just listing. I'm listing the multiples of 117. What I usually do is I'll use my fingers, and I'll say the thumb. You count with your fingers. I'll just count them with my fingers like that, and then be able to kind of do the long division. I know that's weird, It's really fun to do if I was with you in person, but it's not gonna like change anything here, so we'll just keep on going. I don't wanna have too much confusion there. Oh, this is a nice question. All right, let's just change the subject. Uh, Whenever you have a fraction over a fraction, okay. So here's a nice little thing. Whenever you have A over B, and then you have C over D, one way to solve this question is to cross multiply. Who's familiar with cross multiplying? Who's familiar with the idea of cross multiplication? Okay, cool. All right. So cross multiplication really is the way to go with these. I've encountered some situations where teachers don't like students using the phrase cross multiplication or such because it's not really a formal approach. From a foundational approach, what you should do is multiply both sides by 30 and multiply both sides by 60. That would be like the traditional way to do it, the way that is based on the basic rules of algebra, which is really important. But in this case, we're not going to do that. We're just going to do the easiest thing possible, which is this. I'll use brackets because now the numbers are getting a little bit out of control. So we have 60x equals 1200, and I will pick up the pace here. So what 1200 divided by 60. Now this step here where I write 1200 divided by 60, thank you Matthew, is I don't usually write that down, but it's all good. Answer, what's the final answer? 20? Okay. One thing that you can do immediately in the question is you see the zeros here, you could cross them out. You should reduce them. In fact, you could reduce this to 2/3. If you reduce that to 2/3, it does make the question a lot faster. Let's see how the answer would look like if you had reduced it. So I'll take this answer here and just kind of put it on the side. And I'll do the alternative version. Maybe I'll do it in green. Let's do the green version here. And so that at least you can appreciate that the effort that you take in observing for patterns in the question could make your life a lot easier with the algebra later. So, because you're dealing with small numbers. This would be 2 times 30. And you can already see that the answer is going to be a lot easier. Because I could do that. If I asked anybody here, 3 times what equals 60, I should get a response in under 5 seconds, hopefully. Plenty. So it's just an idea, okay? Like if you don't do the thing in green, it doesn't mean that you don't know how to do stuff. It just means that you're going to spend more time. But sometimes when you're looking for shortcuts, this is true also. When you're looking for shortcuts, sometimes the time that you spend looking for the shortcut is offset by just doing the question. So in other words, sometimes you waste time looking for shortcuts. So for that reason, there's a healthy balance between the two. We're not going to try to become philosophers about which way is better. But if I notice something that's immediate, I'll take advantage of it. Like that reducing a fraction, I would definitely hit that step first before doing anything else. Now, here's a situation where you have a fraction equals a fraction, and probably the most strange looking question of today, but all you're going to do is cross multiply. So let's use the highlighter here. We're going to multiply this guy here by this guy here, and then you're going to multiply, I'll do it in yellow or something here, then this guy times this guy. So that's cross multiplication. It doesn't matter which side is which, so I'll just put the 4 first because that's the first number that I read. So it would be 4 times 2x minus 1, and then 5 times x plus 3. I know that some of you are probably like, this is really easy, but keep in mind also that there are people here that haven't done math in a long time. So we're just, trying to be gentle the first hour. As with most units that we've done together, we're gentle in the first hour, and then we turn it up a notch by the third hour. Anyway, in this case, remember to distribute. So we're going to do 4 times that, and 4 times that, and then 5 times that, and 5 times that. So what we're doing is distributing. So we're distributing the 4 and the 5. I'll just say distribute. In this case, if we distribute it in the first bracket, we're going to get 8x minus 4, and then the second bracket, 5x plus 15. Now, this looks like the first question from this section, where we moved over 2 terms to get to the proper place. So in this case, we have 8x minus 5x, and then 15 plus 4. I'm going to highlight those terms just so that you're clear about what I was moving over. So I moved over the 4, and I moved over the 5x. This gives us 3x is equal to 19. Let's leave this answer as a fraction. So the final answer here is, I'll leave it as 19 over 3. Can someone confirm they agree with this number, this answer? Anybody can confirm they agree with this? Thank you, Marco. Thank you, Nicolos. Now, I keep on asking you in these questions, oh, do you agree with me? Can you confirm? Can you do this? Can you do that? But what if I was by myself? What if I'm by myself and I'm solving a really hard problem and I'm really not sure about if I got it right? Is there a way that I could confirm for myself without anybody's help or anybody's assistance, if my answer is right? What could make me feel better to know that my answer is right or wrong? Well, that's how you check your solution. You can check your solution. So I'm going to go back and I'm going to pick a question and we're going to check the solution. So if I go back to the very first question, okay, so just I'm going to go back to question A. So we have this answer here, or I saved it. So how can we check our answer? Any suggestions in the chat? How can we check our answer? Yeah, you can put 13 as x. So what Matthew is referring to is that if I put in 13 for x on this side, I should get the same answer if I put 13 for x on the other side. So what you're checking for is something called consistency. What we're looking for is that the left-hand side equals the right-hand side. So LHS and RHS is left-hand side, right-hand side. So in this case, the left-hand side is equal to 6x minus 21. Just a second, I gotta fix my tabs here. So we have it aligned better. That's nicer. So I'm just gonna squeeze that over. So 6 times 13 minus 21, which is 78 minus 21 is 57. Can someone confirm 57? I'm not using a calculator here, so you'll have to give me a hand. Build up my confidence a little bit. And again, I'm pretending that nobody's here, so no lifelines. Gotta do it by myself. So that's 26 and 31 is 57. So look at that. Good to go. Okay. So if you if you're on your own or if you're writing a test or whatever, and you're like, I don't know if I got it right or whatever, go put x into the equation onto both sides. If you get the same answer for both sides, you're good. Now, if you were to do question E here and try to substitute it there, perhaps in this situation you don't get exactly the same number, but that's expected because this number was a rounded value and you would lose some accuracy. So anyway, here's one more question. We'll do this question here probably, and then after that we'll take a short break because I think that we're getting close to the hour mark anyway. So in this case, we have two fractions present. Now, this is a situation that I was referring to earlier. You could deal with fractions all the way through, or you could get rid of the fractions as soon as possible. And I strongly suggest that we get rid of the fractions as soon as possible here. So you remember I said the left side or the right side, and I said which way do you like better? I'm going to go with the one on the right this time. So I'm going to try to clear the fractions first. Now, what number could I multiply everybody by to get rid of the fractions? Any suggestions there in the chat? What number would do the trick? If I multiplied everybody by 3, would that get, oh, Nicolaus, thank you. Notice that Nicolaus is correct there, is 12. Any multiple of 12, but 12 is the best choice because it's the smallest multiple. It's the smallest one. Anyway, in this case, if I multiply by 3, this will become a whole coefficient. It'll be 1x. But this number here would be 3/4 x. So you wouldn't quite do the trick. Same thing if you hit them all by 4. This would become 1x, but this would become 4/3 x, which is still not good enough. So 12 is the best choice, and that just refers to the LCD. What does LCD stand for? What does LCD stand for? Thank you, thank you, thank you, thank you. I'm turning into an engineer today on you. As you might not know, maybe you don't know or whatever. I am an engineer, literally, so that's what engineers do, but not me. They like to use acronyms. But I'm not really a fan of acronyms because they just clutter my life anyway. We're going to multiply everybody by 12 here. So we'll do 12 times x over 3. Just bear with me as I have to type this out. Minus 12 times 1 is equal to 12 times x over 4 plus 12 times 2. Now I could use brackets here. If you prefer brackets on this, maybe it's brackets are the better choice. Yeah, let's do brackets here. Like that. Then in this first bracket, I'm just going to get my trusted pencil here. So when you have the 12 and the 3, that reduces to a 4. Because 12 divided by 3 is 4. And then here, 12 divided by 4 is 3. So that's the process of clearing out the fractions. I should say clear the fractions, plural. Anyway, in this case, we'll have 4x minus 12 is 3x plus 24. That becomes a situation where we can move some terms over. We're going to move the 3x over to the left, and we'll move the 12 over to the other side. So x is equal to 36. There you have it. So I'm going to just do the check right now. By the way, you don't have to check all the answers. I'm just doing a couple of checks here because we definitely have time to do that. Let's do the check here. So the left-hand side is equal to, if you go here, it's x over 3 minus 1. So I'm going to plant in there the 36 for x. So 36 over 3 minus 1 is 12 minus 1, which is 11. And then the right-hand side, okay, so I'm going to have to just shrink the font on that. I'm trying to get it onto one page nicely. So just bear with me for a second. This should be not a big deal. There you go. The wonders of technology. There you go. The right-hand side is 36 divided by 4 plus 2, which is equal to 9 plus 2, which is equal to 11. So yeah, you see how the check held for us? So at least you know that even if you don't have anybody to bounce the ideas off of, especially, for example, during a test, you can at least you can at least check your answer. So even if you're under immense pressure on a project or doing something, and you end up having a solution that you want to critique, you can always find a way to do that. Anyway, it's 9:49. I think it's a good opportunity for us to take a break. So why don't we resume class at 10 o'clock? I'll see you back at 10 o'clock. So now that we're dealing with an example involving a diagram, it really makes sense to pay attention to how to compare the information in two different ways on the diagram. So what I've done here is I've highlighted all of the lengths individually in yellow, and then I've highlighted the overall length in blue. So what we're going to try to do, hopefully, is solve for x. And once we have solved for x, then we can go back and identify all the various lengths that are asked for, including A, B, C, and D. So let's take care of that together. Any suggestions on how we would set up an equation here? Any recommendations on how to set up the equation? What are your thoughts here? I'll zoom into the figure a bit more, maybe that's the issue. So you see all these lengths here, they have to add up to 15.5. Okay, you're just writing it down. Yeah, just tell me without any numbers, without variables, just tell me what you're gonna do here in the chat. Just tell me without saying any numbers. What would the equation look like in terms of what you would try to compare? Compare what? Yeah, exactly. So you're just adding up the lengths of each of those rectangles. So what I'll say is I'll compare the individual lengths, the total length. The individual lengths are going to be all of these dimensions here. Some of them involve x, some of them do not involve x. So the one at the end there is just 2. These are all in inches. And then, okay, there's 7 of them. So as I read across here, I'll write 7 expressions. So 2 plus 2.5x. Yes, use a decimal. If it's going to be fractions like a half, be my guest. Plus 1.5x plus 2.5x plus 1.5x plus 2x plus 1.5, and that'll equal 15.5. So what I did is I just systematically, I wrote down all of the values of each of those quantities, and because the fractions were nice, they were just like 0.5s essentially, they're all fractions involving a half, then I just made them all nice decimals there. Ultimately, we want to try to collect all the terms that are like. So from here all the way to here, let me just highlight that all in green or something. All of those terms there can add up to one value of one term involving x. So 2.5 plus 2.5 is 5. 1.5 plus 1.5 is 3, so that's 8. So I got 10. 10x plus 3.5 is 15.5. Can someone confirm? Anybody confirm that, please? Thank you. Thank you, thank you, thank you. So 10x, I went a little bit quick there, I'll slow down. So this is equal to 10x, all the green stuff, all the green terms, and then all the black terms, I add them up, I got, so I got 2 plus 1.5 is 3.5. Moved over the 3.5 to the other side, ending up with 2, and then you get a nice number here. So x is 0.2. I'll just say inches, it's fine, or in. Oh, sorry, 12. 12. That was a typo. When I hit the buttons on the keyboard too fast, you know, that's what happens. Okay. So you get 1.2 inches. I would leave it as a decimal. I wouldn't bother turning that into a fraction. But now we have to go back and get the dimensions of A, B, C, and D. I'll move that over a little bit. Which part, Norris? The 12? This step? Which step? Okay, there's 5 steps here. So 15.5 minus 3.5 is 12. Just a second, Matthew. Sorry. Oh, I divide both sides by 10. Is that okay? Okay. So let's get A, B, C, and D. I think Matthew was on the first one. Sanjit. Okay. I'm gonna write down all the steps here for A, B, C, D here so that they're all, I can read them all in one place, in one location. Sorry. So A is equal to 2 plus 2.5x. Just bear with me, everybody. I know these are very tedious, but I also don't want to lose anybody in this conversation. So then A is 2 plus 2.5x, but x is equal to 1.2. So A is equal to what? Sanjit has a 5 there. Can someone confirm the 5? Anybody want to confirm? Thank you, Matthew. Okay, and then B. Now, B is equal to all three of them. You could do it that way, or you could say that B is equal to A plus 1.5x. I'm just fine to do all three of them. I'll do all three of them. So I'll say 2 plus 2.5x plus 1.5x, like that. And then before plugging in the number, I would take 2.5 and 1.5 and add them to get 4x. So I'm seeing in the chat here that, yeah, exactly. So Matthew's saying the same thing. Yeah. Yeah, that's fine. So I think we're good to go there. I'm going to plug in, like what I'm saying is you can get creative here, but I'm just doing it with the basic values of x because it really isn't that much of a penalty with the algebra. So 4 times 1.2 is 4.8, plus 2 is 6.8. Where did I get the 1.2 from? Okay, Marco, just a second. I got it from here. Is this what you're asking? This 1.2 or this 1.2? So if it's this one over here, I'm plugging in the value of x because now we know what the value of x is. Yeah, once you have the value of x, you can go to the diagram. In fact, if you want to make your life a little bit easier, possibly, we know that x is 1.2. Feel free to put it in everywhere. Put it here, put it here, put it everywhere. Fill them in. Yeah, exactly. Nice, Sanjit. So what I'm saying is if you want to put 1.2 here for x right away and just get numbers, then add up the numbers to get b. That's totally cool. I'm just doing them on the side here because it's just extra practice with the algebra. So C and D, and then we're going to be done with this question. So I'll just squeeze that down there. Just bear with me, everybody. Sorry if I'm like being a little bit extra here. Functions, no Sanjit. This course is strictly algebra and numeracy measurement, etc. And then in the next course, we'll be doing mostly geometry and trigonometry and physics. So the second course is geometry, trigonometry, and a little bit of physics, if you're wondering, but no functions. So let's figure out C now. So C is equal to 2x plus 1.5. But we know that x is 1.2. Anybody have a value on C? 3.9 confirmed. Totally agree. And since we're here, we can also get D. I'll just put D right here. So D is equal to, oh, thank you, 1.5x plus 2x plus 1.5. So that's 1.5 times 1.2. Wait. I'm going to simplify that first. You can also take a shortcut, as you see there what Matthew did, is they probably added to the previous answer. So the way that I'm doing it here, again, is not the most efficient way for these last steps. I'm just trying to show you that you can rely on the algebra before you plug in the numbers. Maybe it saves you a little bit of time. So 5.7 on the last one. Thank you. Well, that was exciting. That looked like a lot of fun. Hopefully I didn't scare anybody away too much. But anyway, these questions are very useful, especially if you're going to be doing any type of machining or any type of project where you have to have a lot of working parts together. The next question is actually really a good one as well. It involves um, a little bit more creativity in terms of the actual algebra. So hopefully we can get through this question without too much stress. I'll just pause for 30 seconds and give anybody a chance to finish writing down anything that they might have not gotten on paper. So I'll just wait for 30 seconds. Okay, so let's do one more question, another one involving a diagram. In this situation, we have the following. I'll zoom into the diagram shortly. So we have this plate here that's 5 inches long, and a couple of holes are drilled into it. The first hole has a diameter of D, and then the other hole has a smaller diameter, which is D less 0.6 inches. So it's 0.6 inches smaller in diameter. And then the objective is to find the value of D. So we have a nice little diagram here we're going to play with. I'm just going to move the diagram over here. Just get it right in the middle, you know. So let's see what we can do with this. In the similar fashion to the previous question, we know that the overall length of this shape is 5 inches. And then we have the individual lengths. Here we go. We have 5/8. And then we have this length here, which conveniently is D. And then we have something weird happening. There's an overlap. You see how these guys overlap? So that's a little bit of an issue. And then we have a 1/2 inch. So what I'm going to do is, in yellow, I'm going to highlight all the easy stuff. These are things that are easy for us, okay? These yellow things here. Remember, this yellow one here is D. So that value D goes in there. So what do we do with this? Any comment in the chat? What the heck is this length here? What the heck is that length? It's the radius. That's right, Sanjit. I don't know about the numerical value, Matthew. You might be like 5 steps ahead of us, but yeah, it's the radius of this shape here. So what I'm going to do is I'll say it's half of D minus 0.6. Yeah, that's negative 0.60. Yeah. I wrote it down here on the side though. Just read the stuff I have in green if it helps. Now instead of a half, let's put a decimal there. And I'm just going to do a quick algebraic step here. So I'm just going to do this on the side, and then we'll deal with the overall question. So just on the side here, I'll retype that a little bit nicer. Exactly, yeah, I'm going to do that right now. Literally what you're saying, I'm doing it right now. So we have half of 10 minus 0, D minus 0.60 is equal to a half of D minus 0.30. And I'll just write it as a decimal, so that's 0.5D. If anybody here is getting irritated with a D and they want to use the letter X, feel free to use the letter X. No problem. So anyway, that's just a little bit of side math. Now we can go and talk about the overall situation. We know that the overall length of this apparatus is 5 inches. So we have here 5/8 plus D plus, and I'll write it the way it's in the question, 1 1/4, even though it pains me to write that down, plus what we just wrote down, 0.5D minus 0.30 plus a half equals 5. So all of those quantities there are related to the question individually. So all I did was I just lined them up and added them up. The one thing that is really frustrating here is the mixture of fractions and decimals. So on the next line, I would encourage you to write everything as a decimal or a fraction, but not both. 5/8 is 0.625. I gotta spread that out a little bit there. 1 1/4 is 1.25. And a half, of course, is our good old friend 0.5. So what you want to do now is kind of filter out all of the terms that have a variable in them. So this D here has a variable in it right there. I'll put it in red. And then this guy over here is going to be in red. So let's take all the terms on the left that have a variable and add them together. So the like terms, which are the ones in red, are 1 and 0.5, so 1.5D. And then you have a bunch of decimals to deal with. So we have 0.625 plus 1.25 plus 0.5 minus 0.3. So that's not exciting. Anybody want to grab a calculator for that? Can someone confirm Matthew's answer, please? Thank you, Matthew. Can someone confirm that number, please? Add up all the numbers here in black, not the red ones. Ignore the red ones. Thank you, Sanjit. So we're good to go there. We have an answer of we have a simplified equation as follows. The question, remember, is just to find the value of D. So we're basically, once we have D, unlike the previous question, we're good to go. We don't have to do extra. So in this case, let's move over the constant. That's going to be 2 point something. Thank you. And then divide that by 1.5. And hopefully the answer is a nice number. That's what happens when you type too fast. You put the decimal in the wrong spot. Thank you, Sanjit. Thank you, Matthew, especially for you. You two knocked this one out of the park. Much appreciated. How did I get 1.5D? Because this is D here, it's 1D. And then 1D plus 0.5D is 1.5. Cool. And you're welcome. And ultimately, yeah, thank you, Sanjit. If you don't have a coefficient in front, it's automatically assumed a 1. It's assumed to be a 1. It's kind of cool. So in this program, this course and the other course, the Math1136 course, in the past, for students that have taken a university math or something in college before, there is the possibility of an exemption test, an exemption, sorry. So for the student to have an exemption, yeah, Sanjit, it was mentioned at the beginning of the year. That's okay. You're already here now. But you could possibly apply for an exemption in the second course. It actually works out well because if you apply for the exemption in the second course, then you would be exempt from from that one. See, yeah, that was actually in the beginning of the course outline as well. It's right in the course outline, Nicholas. You know what's funny is I mean students that have taken a post-secondary math, they'll say that they want to do the exemption, but actually it benefits them to be here anyway. Just a second, I'm gonna just check something. plus, in all honesty, it would not be the same. It would not be the same if I didn't have you here in my class anyway. Because I mean, of the many students that are here, and everybody's been very helpful. You know, it's nice, especially with Nicholas and Sanjit, Matthew, and many others, that if you're not here, you really do bring such a benefit to the class. So, you know, don't leave, don't abandon us, stay with us, okay? Well, I know that other people are seconding that, especially those that are like, okay, I know what I'm doing, but I don't want to type the number in the chat. So you're doing everybody a service. Okay, anyway, all jokes aside, I love having you guys here, so don't go. So we're gonna move on now to the next section, which is weird. It's a weird one. The number of solutions that an equation can possess. So the author of the book here talks about something saying here, no solutions or infinite solutions. So there is the possibility that when you create an equation, or when you're given an equation, that equation might be set up in a way that there's no answer, or there's an infinite number of answers. And you might say, well, how's that useful in real life? Um, it's useful in the sense that it's whenever you encounter something like this, when you encounter a situation where there's no solution, it could be a real life problem that does not literally have a solution, where you cannot, it's not possible to solve it. For example, let's say that you want to travel from here to Montreal, and you set up an equation that you get a negative answer. Well, that means that it probably wouldn't be possible under the conditions that you specified, whether it be speed, distance, or some other type of situation. Or what about infinite solutions? An example of a real life question with infinite solutions would be like providing supplies to a site. Is there only one way that you could deliver material to a construction site? Is there only one way to do that? Of course not. There's infinite ways, because you could have all kinds of different scenarios with equipment being delivered. You can do different routes. Routes could have different costs. They could be at different days, different times. The payment might vary depending on all of these things. So all of those situations in real life, there's never just one answer. So that's why it's nice to see how that is reflected with algebra. We're not going to be setting up some type of ridiculous equation that is going to involve a case study here. I'm just going to stick to some basic algebra and show you how to identify situations where there might be, or where there are no solutions possible or infinite solutions possible. So to do that, we're going to take a look at some exercises in the section here on this situation. So if we move ahead to questions on page 16, we can talk about this in more detail. So on page 16, there are several exercises here, and we're going to explore these all together right now. And I'll talk to you I'll explain to you how you know if there's no solutions or infinite solutions, or if there's a unique solution or more than one solution, etc. I'm noticing that there are several questions here, and in hindsight, I think it would be best if we did all questions here. So there's 10 questions. I feel that we should just solve all 10 of them. When I planned out the semester back in August, um, I didn't anticipate how fast or how slow I'd go through the material. So we're just gonna do every single question here, and then once we finish, we'll call it a day. So, and then on Friday, of course, we'll finish off the last two sections. So we're doing these questions, and again, the page reference is page 16. So I'll write down the page number momentarily. But we're going to do every single one, and I'll talk to you about special situations involved. This is going to be weird for some people, but it has a very important implication with algebra. It helps you figure out if you set up an equation wrong, really, as far as you're concerned. So question A, I'm just going to copy the question down, but not write down the question letter. So question is A is 4x plus 7 is 4x minus 6. Okay, so what is the strategy that we've been using all along? Sanjit, you're quick, my friend. I'm going to go through this systematically. What does the algebra say? Let me know, someone else in the chat that hasn't really talked too much today. What would be the first step that we've done in the past? What did we do in the past? We moved everything. How do we move things around? How did we move things around? Anybody? Yeah, move the 4 to the left and the left to the right. Yeah, you're just moving the thing. Thank you, Marco. You're just moving the things around as you normally do. So I'm going to take this 7 here. I'm going to take that 7 there, and I'm going to move it to the right, and I'm going to take this 4x, and I'm going to move it to the left. Let's see what happens here. 4x minus 4x equals negative 6 minus 7. What do you get on the left? What does the left side equal? What do you get on the left side? 0. What do you get on the right side? Easy numbers, 13, negative. Okay, so here's the final situation. If all the x's cancel, okay, so if all of the x's cancel or disappear, and you end up with an inconsistent statement, then there is no solution. What do I mean by inconsistent? What does the word inconsistent mean to you? What does the word inconsistent mean to you? This is not an English class story. Inconsistent, I'm talking about does not make sense, okay? In the context of math, does not make sense. See? Question for you. Does 0 equal negative 13? Does 0 equal negative 13? Of course not. That's garbage, right? That makes no sense. See? Does not make sense. Inconsistent. No solution. So you might say, well, you know, is that what would be a situation where the x's disappear, but then you do get an answer? Well, that'd be question C. We'll actually skip over to question C actually, because B is the same thing as A. So let's do question C. 4x plus 7 equals 4x plus 7. What the heck? What the heck? Let's follow the routine. Let's just follow the routine. So you would have here 4x minus 4x equals 7 minus 7. What do you get on the left side? What does the left side become? What does the right side become? Okay, question for you. Thank you, Cosmo. Question for you. Does 0 equal 0? Is that true or false? Is 0 equal to 0? Is that true or false? Good. So then what this is mean here, if all of the x's cancel out, so there's infinite solutions here. And it's really easy to see that, okay? Whenever you see 0 equals 0, whenever you see 0 equals 0, just remember that means infinite solutions. That's all you got to remember, okay? And if you get 0 equals garbage, so if you get 0 equals garbage, then there's no solution. See here, that's garbage. That statement makes no sense. So that's the heart of it. And you see this even in the most advanced math. But whenever an equation ends up being 0 equals 0, just know that it means infinite solutions. So any value of x works here. You pick a value of x, it'll always work. This means that any value of x is a solution. And that's the heart of it. These two examples represent the ideas that are explored in this section. Whether you get 0 over 0, 0 equals 0, or 0 equals something else, you just need to be aware of what's going to be the consequence. So we're going to do some more questions now that follow this idea. And ultimately, you're just looking for the 0 equals 0 or 0 equals something else, and saying no solution or infinite solution. And within the questions that we continue with here, sometimes there's some ones that will have an answer. It's just that they're kind of, you know, sprinkled in there to keep you I guess just on your toes about the extra stuff here. So we're not just going to be doing 0 infinite for these examples. So the next example that we'll cover is example D, 3D. So we have here 4x squared plus 7 equals 4x squared plus 7. Now, D is infinite. Thank you, Sanjit. Let's walk everybody through that, okay? So when you look at this equation, you notice how the right side and the left side are identical? That's how you know that it's infinite. But let's do it with some algebra. Let's show some steps here. So we're going to move over the 4x squared, and we're going to move over the 7. And you end up with 0 equals 0. Infinite solutions. I'm going to pause, give people a chance to write that down. All I'm doing right now is just copying the questions down. So just ignore me. If you need more time to write this answer, no problem. I'm just copying down the next couple of questions, okay? I'm just preparing for the future ones. Okay, so hopefully I had a chance to deal with that question. In this next question, we have, oh, nice. I'll catch up to you, Sanjit. We'll all catch up to you in a second. In this question here, what do we do with this stuff here? What's the first step, everybody? What would you do here in the chat? Any suggestions? Yeah, you can move them all to one side. I'm with you on that. I'll do what you're saying, Matthew. I'm gonna do one step first, just because I'm lazy. I'm too lazy to move everything over. So I'm just doing what Matthew said, but I'm gonna just combine them all first, if you don't mind. And then you get that. Now, it's difficult when I'm typing this here because it doesn't let me align the equations. So unfortunately, I like to line up the equal signs, but I don't have that luxury here. So sorry about that. So anyway. So what's the answer for question here? Well, this is question number E. This is question E. But what do you get? What's the final answer here? How do you get rid of the 7? You divide by 7. So the answer is actually just 0. So you see here, in this situation, the x's didn't disappear. Make a note of that, okay? In this question here, x's don't disappear. The x remains. Therefore, there is a potential for a solution. Let's say, therefore, we can use the traditional approach as earlier, okay? So this is really just a normal question. This is just a regular question here. In the next question, though, maybe we actually get something weirder. And I think Sanjit had indicated, or kind of, hinted at the possibility of something weird. So let's see here. We're going to take the left-hand side and expand that. And at this point, there will be some people that are a little rusty at this. I'm just going to delete that. So anyway, how do you deal with this? How do you deal with these brackets here? You're going to distribute this, okay? So some people haven't seen this for a while again. So we're going to go slowly here. We do x times x and x times 5. And then after that, you'll do 5 times x and 5 times 5. So this is a distributive property. If you distribute those terms out, you get x squared plus 5x plus 5x plus 25 is equal to this. Which eventually becomes this. Yeah, you end up with infinite. And you know, you can save yourself some time here. If you don't want to move everything around, you can cancel. So let's try to do a cancellation here. Maybe it's a little bit more economical. See, this x squared cancels with this x squared. This 10x cancels with this 10x. This 25 cancels with this 25. So we can actually apply cancellation here and see that it's 0 equals 0. Sorry about the scrolling there. It does it automatically when I try to highlight something. For some reason, it'll just scroll. Anyway, I'll give you a moment to take down that answer, and then we'll try a couple more versions of the same question. So I'll just give you another 30 seconds to write down anything you need to write down there. It's my preference to do this cancellation type of thing because it's faster. We could have done this earlier with the questions as well. Yeah, we'll get there, Sanjit. Okay, we're gonna move on now to question G. So G and H kind of go together, which is cute. So I'm just gonna put G here, and let's just delete all of that. So the only difference with the G is that the number here at the end is not a 25, it's a 23. So this is a 23. So otherwise it's the same kind of question. So in question G, the 25 turned into a 23. So when you expand out the left side, which is something we just did in the previous question, you end up with the following. You end up with the following. So let's take a look here and see what happens. I'll use the cancellation approach because it's a lot more fast. So this x squared cancels with this x squared. This 10x cancels with this 10x. And then we end up with the following statement. 25 equals 23. If you prefer, you could move the 25 over or the 23 over, and you could say 2 equals 0. But this is basically, it's already garbage at this point, because I hope that we'll all agree here that 25 and 23 are not the same thing. So we don't have to write 2 equals 0 at all. We can just say right now it's inconsistent. See, the idea is that the x is canceled. But whenever those x's cancel, then you know that there's a situation where there's no solution, especially if you end up with an inconsistent statement. Okay, so we're going to try question G now. So G is a variation, again, just tweaking it a little bit. So if we were to write G here, then the difference is that this is 8x and 33. So in this situation, we do the expansion on the left, and then that equals this stuff here. And I hope you don't mind me copying and pasting, because it's very much the same procedure as the previous two questions. So we end up at this location here. Now, it's nice that we have these three examples kind of in sequence, because they show you all the versions. We had an infinite solution, we had a no solution, and in this case, we'll have a place where there's actually a single solution, just a regular algebra question. See, the x words cancel, and you end up with an example that's not different in terms of its style or structure. It's not different from our very first question today. So it just has different coefficients, but the structure is very similar to the first example we did. So we can move all the x's to one side. and move all the numbers that are, all the terms without an x to the other side, and end up with something nice. So 33 minus 25 is 8, and then x equals 4. So you see that just because you have a more complex equation doesn't mean that you can predict what's going to happen right off the bat. Sometimes it works out, sometimes it has infinite answers, sometimes it has no answers. It really can have anything. So that was question H. And we had a comment in the chat. Sanjit mentioned that I is weird. So this actually, we're going to do I shortly. I want to do J first, if you don't mind. I'm going to do J first, and then I'll do I at the end, because I is really a preview of the next lesson. So let's do J first, and then we'll do I at the end. It is possible for the x's to survive and to have no solution, but that would be very rare. We're not going to see something like that in today's class. So let's do question J together. So J is algebra fun. We have x plus 1 squared minus 10 is equal to x plus 2 squared minus 20. As far as you're concerned, just expand the heck out of both sides. Okay? So that's x plus 1 I'm trying to copy and paste it. I'll just type it. Times x plus 1 minus 10 is equal to x plus 2 times x plus 2 minus 20. So we're going to distribute the two brackets there and get x squared plus x plus 1 minus 10 is x squared plus 2x plus 2x plus 4 minus 20. And anything obvious there? We notice that the x squareds cancel. So we end up with a linear equation. And in this case, this linear equation has a unique solution. So we'll have here 2x minus 9 is equal to 4x minus 16. So we're just collecting the like terms on each side separately. And then we're going to move all the x terms to one side and all the constants to the other side. So 2x minus 4x is equal to negative 16 plus 9. So negative 2x is equal to negative 7. Can someone confirm they have the same answer? Anybody agree with this answer? Thank you, Cosmo. Thank you very much. So, thank you, Nicholas. So we're gonna do one last example, but I'll give you, like I said, I'll give you 30 seconds to jot down anything you need here. Don't worry, Nicholas. That was me about a month and a half ago. My building, Rogers was doing all kinds of weird things out there, and we were having like all kinds of disruptions. So I ended up having to go to my parents' place to do the lessons, which is good food, but I'd rather be in my office doing the lesson. Anyway, let's see what's going to happen here. We have this last question, which is a preview of next week's class. Okay, so this next question, which is x squared equals 49, this is our last question for today. So I'm just going to put it up here. A preview of the next class, okay? If you have x squared equals 49, what does the answer equal? Or how do you get rid of the squared? Okay, So what's the answer to this question? X squared equals 49. X equals what? Demirland, right on time, my friend. The answer is plus or minus 7. See, it's very common for people to just write down the 7, but does anybody, who remembers that you got to put plus or minus? Who remembered in the chat there? Let me know. Did you remember plus or minus? In other words, what we're saying here is that we have x equals the square root. You don't have to write this 2 here. See this 2 here? I'm only putting it there because I want to show you more general things next time. But that's the answer. It's the square root of 49, but you need plus or minus. We're going to talk about questions next class that involve higher order roots, okay? So not just square roots, okay? So next class, we're going to deal with higher order roots. And also with positive and negative numbers. So stuff like this. Square root of, well actually, I'll just bring this up next time. We're good to go, I think. You guys have class soon anyway. So that's enough for today.